writing transformations of quadratic functions. So yesterday, or Friday really, we talked about looking at how they move. When we look at the function, how does it move up, down, left, right, vertical stretch, vertical shrink, horizontal stretch and shrink, as well as reflections across the x-axis or the y-axis. And really just looking at the function and determining how is it moving, how is it changing from the original parent function y equals x squared, or our x squared function, to this one here. Now they do give us this form again, but really I like a parentheses bx minus h squared plus k. I really like this version better because the one that I wrote down really takes into account our horizontal stretch or shrink. The other one doesn't have a value for it. We just have to assume it's there and go from there. So I like this a little bit better. As we saw the other day, k is our up or down. H is the left or right. B has a few features. It is a reflection across the y-axis. I'm just going to write y-axis, but it is a reflection across the y-axis. Because y'all can rewrite this down, but you do have it in your notes already. It should be on the first page. Yeah. Or a horizontal stretch slash shrink. And there's nothing wrong if you want to rewrite it, because I did that in college. I rewrote everything the professor put on the board. And the last one is our A. Now this is a reflection across the x-axis or a vertical stretch or shrink. John Brown. I did. Okay. So what we're doing today is actually applying these transformations. Let the graph G be a vertical stretch by a factor of 2 and a reflection in the x-axis, followed by a translation 3 units down of the graph y equals, or f of x equals x squared. Write a rule for G identifying the vertex. Okay. So I'm realizing, because it's wanting to write a rule for G, essentially apply those transformations, which we've done before. We did that last chapter in 1.3. Now, identifying the vertex is something new. And I'm realizing as I look at this here. Really, the vertex is h comma k. Is that h comma k value. The value of h and k is our vertex, no matter what the function is. The only exception exactly is if we have a b value and an h. If we have a b and h value, like we saw Friday, where it messed with the movement left and right, because we had the function, I think it was like negative 2x plus 6, and we had to factor the negative 2 out of both terms to see it. That would be the only case where it would affect it. Now, Let's actually apply the transformations, and I'll point this vertex out. So when we look at this here, let the graph G be a vertical stretch by a factor of 2. That's what we're going to do first. Vertical stretch by a factor of 2. Well, that's what we did last time, wasn't it? One of the ones that we had from chapter 1.3 where we talked y equals a of x, a f of x, y equals f a of x when we were plugging them in. Vertical stretch is this one here. Well, our factor of a is what? 2 times f of, well, what is f of x? X squared. So we'll have 2 times x squared, which is 2x squared. Now, what do we want to call this new function 2x squared? Well, they want it to be g of x at the end, yes? So what? H of x, it doesn't matter. Okay. I'll get a highlighter back up. And then what? A reflection in the x-axis. Okay. Well, a fraction across the x-axis is just y equals negative f of x. Because again, I'm just recalling back from the last chapter. Well, here we won't really use f of x. We're going to use h of x. So we're really saying negative h of x. What is h of x? Multiply these together, we just get, give this a little space, negative 2x squared, yes? So we've done the vertical stretch by a factor of 2 and a reflection across the x-axis. Reflection in the x-axis. Yep. So we can call this m of x. And exactly our last one, y is equal to f of x plus k, because that's our up and down, our vertical. But we don't have f of x, we're using m of x, and our k is going to be minus 3 because we're going down 3. Now m of x is negative 2x squared minus 3. And that's it. Now vertex, the vertex is the point h comma k. Well, we know what the k value is. The k value would be negative 3, because in our general form, outside is k. Inside the parentheses is h, yes? Do we have parentheses at all? So the value has to be 0. So the vertex for this would be 0, negative 3. Now the vertex is the lowest or highest point on a parabola. So when we saw the parabolas the other day, how it came down to a single point to start off with, its vertex is 0, 0. It starts off on the origin. It is the minimum or maximum point of a parabola. And that's it. That's all we have to do for this here. Yes, sir. Yeah, so the rule, quote unquote, the rule is g of x equals negative 2x squared minus 3. So in 1.3 where it said write the function g of x, write the rule, those are the same thing. Those are the exact same thing. And as we go through Algebra 2, there's going to be a lot of things that are the exact same thing, just phrased differently. Because if we want to find the solutions of the quadratic function, will be the same as finding the zeros, finding the x-intercepts, are all the same thing. It's just different ways to phrase what we're looking for. But they all will be the same value. Questions on this here? Let's get you to go away. There we go. Let G be a vertical shrink by a factor of 1/2, followed by a translation 2 units up of the graph of f of x equals x squared. Write a rule for G and identify the vertex. So again, exactly, when we write the rule, we're really just writing what the function is after the transformations. Well, vertical shrink by a factor of 1/2. Well, again, this is our y equals a f of x. Well, our factor of a is just 1/2. We don't have to do anything to it. F of x is, which is just going to be 1/2 x squared. And I'll just call this h of x. Done. Followed by a translation of 2 units up. So we can use the y equals f of x plus 2. Well, we don't really have f of x. It's really going to be h of x plus 2. So we'd have 1/2 x squared plus 2 is going to be our g of x. Now, if you notice, most of these, it's just multiplied the x squared by 2, added 2. Just because how they set these up and worded these, really, we just can throw them in and we have the function. Yes? Now, if it had done it the other order, let G be a translation of 2 units up of the graph followed by a vertical shrink by a factor of 1/2, it would be different. Because remember, with our vertical shrink and stretch, it applies to everything in the function, the overall function. So if we'd had x squared plus 2, the 1/2 would affect the x squared and the plus 2 would affect both. So that's why I keep us with this way here, not just, okay, we can throw it in these spots and we're done, because the order of what this does matters, as we saw in 1.3. Yes? Because where we did it the one way and I flipped it and it changed the function if we do it in a different order. Questions on this here? Well, hold up. What did we, the vertex, 0 and 2. Did we move this function to the left or to the right? No. The starting function is just x squared. Its vertex is 0, 0. We just moved it up 2. So the vertex just went up 2 from 0, 0 to give us 0, 2. It just gives us the bottom of the function. Let the graph G be a horizontal shrink by a factor of 1/3 and a reflection in the y-axis, followed by a translation 2 units up of the graph f of x equals x squared. Write a rule and identify the vertex. Now, again, if we wanted to, realistically, we could plug everything in and be perfectly fine. Because the big ones that this really affects and change is if I have a horizontal movement left or right, followed by a horizontal stretch or shrink, because that would affect what it looks like. If I have a translation up or down, a vertical translation, followed by a vertical stretch or shrink, we've seen that that affects how it looks. because those two cases change how it looks overall. So here, horizontal shrink, reflection across the y, those won't change the order in which I do it, because if I do the stretch first and then reflect, or reflect and then stretch, or shrink, here, it's not going to change it. But let's still do it step by step, because if we talk about a horizontal shrink, nice, so I can write y equals f of a times x. What is our value of a? Because they told it was, what do we plug in? 3 over 1, which is 3. Now they told us the function was what? X squared. So really we replace, because we don't have x anymore, we have 3x. So it'd be 3x squared. Yes, if we wanted to, it is perfectly acceptable because I only have one term there, yes? So I can multiply that. 3x, 3 squared is 9, x squared is just x squared. Now at this point here, because we're not really solving for anything, we're not trying to find what value of x will make the function equal 0, we're not solving for a specific value, doing it this way is fine. Now, you don't have to write this down. If we had x minus 1 squared, I'm not squaring this, because if I wanted to square it, it would be x minus 1 times x minus 1. It's multiplied by itself. Well, if I'm trying to find the vertex, the negative 1 is the h component of the vertex, yes? If I square it, do I lose that? Yes. So if it's in vertex form, and I'm wanting to find the vertex, and I have that value of h already, leave it. Here, 3x, do I have a value of h in there? No, it's just 3x, yes? So here squaring is fine. If you want to leave it alone, as 3x parentheses squared, you can do that too. Okay? Well, let's just stick with the pattern that we've had. We'll call it h of x. Reflection across the y-axis. This is y is equal to f of negative x. So here, well, we have h of x, so we're really talking about h of negative x, yes? Do we want to stick with the 9x squared or the 3x parentheses squared? Either one. So here we'd have 3 negative x squared. 3 times negative x would be negative 3x squared. Put a line. If you use the 9x, it'd be 9 parentheses negative x squared. Well, again, I just have the negative x squared, yes? Negative x times negative x is just x squared. I'll call it m of x because we're not quite done. What else did it want? Followed by translation of 2 units up. Y equals f of x plus k. Well, here we really have m of x, and it would be plus 2. Yes? Well, m of x is our negative 3x squared plus 2. Now, if we did it with the 9x squared, we'd have 9x squared plus 2. Because really, we're just adding 2 to the end, yes? And I think that's the last problem on there, isn't it? Okay. This is our parent, parentheses, negative 3x squared plus 9x squared. Turn both of those off. Pull this over. Okay. Now the last thing we need is the vertex. And what would the vertex be? So we need the h value, yes? H is inside the parentheses, being added or subtracted from x. Do we have that? 0. Because bx minus h. Since inside the parentheses we don't have anything added or subtracted to x, because we do have the negative 3, but the negative 3 is in the spot of b, not h, so that doesn't affect it. Now the plus 2 on the outside would give us a vertex of 0, 2. Now in either one, this is actually, because for 9x squared plus 2, nothing inside the parentheses, so it's 0. And the plus 2 would give us plus 2. So we're good with the vertex here. Now, if we're good with all that there, the reason that I pulled this up, Desmos the graphing calculator, is I want to look at the graphs. It'd be helpful if I actually had both of these back, so I don't draw unintentionally on it. So this here is the function, parentheses, negative 3x, close parentheses, squared plus 2. So that's the one we found, yes? Now if we look at the vertex, so for the original one is at 0, 0. The new vertex is at 0, 2. Now we also had 9x squared. Well, the negative isn't there anymore, yes? And I have it right here. You all see that right there? The fact that the blue one is showing up right on top of the green. So the exact same function. They're the exact same function. The only time that really negative reflection across the y-axis makes a difference is if it's away from the y-axis. Because as long as it's along the y-axis, any point to the right of the function is mapped to the left. Any point on the left is mapped to the right. It's mapped onto itself. So we don't see any change. To where if we, right there, say if I did plus 1 here, so we get this function plus 1. Now, I'll take the 3x out. Squared plus 2. I didn't even include the, okay. Let's remove this. Let's take this, copy, A, B, and negative. Okay. So I took the basic one and reflected it across the y-axis. Y'all see what, now that there is a change? Because now every point is reflected across this line. Since it's not on the center of it, it's not reflecting on top of itself anymore. vertex, instead of being at negative 1, 2, is now at 1, 2. It will reflect. But if it's on the center, if that vertex is on the y-axis, it won't show anything. And as we'll cover tomorrow, that's because the vertex is the line of reflection. It reflects. If you notice, any vertex or parabola is always the same shape going either side. So if we reflect it across that line, we get the exact same function. So it doesn't really change anything. But, well, let's go back over here. That is it for 2.1. So I broke it up into 2 days so that we can actually delve in to that deep enough. Now, if you're wondering why I continue to do this step by step instead of just plugging it in like we have for these here, I do that specifically so that when you finally do hit a case where the order does actually matter, it does influence one or the other, you're not having to do it absolutely different because of this setup or this way. Doing it the way that we've been doing with the y equals will work every single time, no matter the order of the transformations. I don't see why we need to go through and learn, or y'all learn a way that works as long as the transformations don't affect each other, and then learn an entirely different way for when they do. Why not just learn it from the start for how it works, for the way they affect each other, because it works for both ways.